the assignment was uploaded yesterday and there was an announcement. So if people have not taken a look at it already, they should go and take a look at the assignment. It's due on 23rd of October.
So given you 2 weeks time. So I think Madhuka's point, I guess your point is that by taking a look at it, people who it may help people to form ideas about the kind of systems that they want to design.
Certainly.
Right?
Yeah, certainly.
Both from the point of view of getting started on the assignment early, as well as trying to get.
Yeah. Also, if there are any questions, feel free to send an email. So, yeah, that's all that I wanted to say.
Sir, can we generate data by using method other than Z3?
No, for this assignment, certainly we want you to use Z3 because there was this component of doing it by Z3. It's fun. So why don't you try doing it with Z3? Why do you want to? Yeah, I mean, for this thing.
I haven't understood how you can generate the data using Z3 because Z3 just gives you a satisfying assignment, right? It does not give you various satisfying assignments.
Yeah, so you should think. So what you have to do is, not sure if that was covered in the Z3 demo. I mean, if you can block the an assignment, you generate one assignment. The way you do that is you generate one assignment and you write a simple while loop, okay, where you block each assignment and keep generating more things. Is that how you generate, or is there a better way to generate? I know some solvers give you something called MaxSat and so on.
Yeah.
So give you multiple assignments simultaneously. So did you use any of those features? If so, can you?
So you need not use Z3 for everything. See, the entire data need not be an output from Z3. So as I have said in the assignment also, the fact that from a given configuration, whether player 2 can play a move and win is something. So basically, to decide whether a configuration is good or bad has to be done using Z3. And this question of deciding whether a configuration is good or bad is really, if you think about it, it's just an existential query. What is the existential query? The query is that, does there exist a move for player 2 such that it can win from this configuration? Now, this is a simple existential query. So you have to make multiple such queries to Z3. So the only exercise that we mandate that, I mean, of course, you can use Z3 to do more. For instance, you could block a configuration and get another configuration from Z3. You're free to do such things, but the only thing that we mandate, or this assignment mandates, is that you use Z3 to decide whether a configuration is good or bad. Now, the definition for a configuration being good or bad has been given, and that is what you need to check using Z3. And if you really try to see the logical formula there, you will see that it's an existential query. So you can make this existential query using Z3. It's a very simple Z3 query. I have actually done this and checked it.
Yeah, but still, his point about having to generate multiple instances, satisfying instances remains, no?
Yeah, so that can be done programmatically, right?
Yeah,
so
that's what. Yeah.
Yeah, so there are not too many configurations. You can, in fact, enumerate the configurations and decide whether a configuration is good or bad using Z3. Does that answer?
No, but then are you okay, even if they, generated it completely without using Z3?
No, so the configuration has to be, so whether a configuration is good or bad has to be decided using Z3, as I have said in the assignment. You can generate configurations, but the classification has to be done using Z3 for the training data.
Yeah, so your answer is they can generate the training data outside of Z3.
So the training data is basically some number of configurations
Correct.
followed by their classification, which is either a
Correct.
configuration is good or bad. I'm saying
Yeah.
that for the classification, you must use Z3. For creating those configurations, you can either use Z3 or you can choose not to use Z3. It can be programmatically enumerated. The classification must be done using Z3.
Classification means?
Classification means, given a board configuration and given a move for player one, you need to decide whether it's a good move or a bad move, right? It's a good move if player one wins immediately. It's a bad move if it allows for player two to win in one move from there. So these things have been defined in the problem.
Yeah.
So the classification, whether so for instance, so earlier, if you remember the primality example, you can, it's like, you can generate all the numbers from 1 to, let's say, 255 or 0 to 255. So you can programmatically generate those numbers from 1 to 255. Now, how do you know whether a number is prime or not? You write your own algo to know whether a number is prime or not. And that is what you present now as the training data. For this one, I'm saying that you can do similarly, generate all the configurations however you like, but how do you decide whether a configuration is good or bad? For that, you should use Z3. Am I making this clearer, or is it just getting more confusing?
Okay, so I can generate all configuration by some other method I like.
Correct.
And to decide whether it's good or bad, I must use Z3.
To decide whether it is good or bad, you must use Z3.
Yeah, because
So
that,
first,
I mean, because otherwise it is kind of error prone. So, I mean, that is one, but it's also interesting to specify those constraints as what he has described has been described in the assignment. And then you can make a query out of it and then try to generate that.
So how many possible configurations are there?
For that, you have to generate multiple satisfying instances, correct?
Yeah,
there are not that many possible configurations, right? We can just generate all of them and all of the moves. Like we can have all possible combinations. It'll not be that large, right? Like it'll be
No, the largeness is not the question. His question is, should it be done by Z3 or not?
Yeah. I'm talking about like it'll be almost like doing it without neural networks. If we have like the training data contains all possible things.
It is, of course, it is not doing without neural network, because you don't want to generate the correct answers from neural network, because neural network can never have, there's no guarantee you get 100% accuracy. Therefore, that's why you have to generate it independently. I mean, I didn't understand that.
I was talking like since there are like nine cells and each can have like 3 different values, so they're like 3 to the power 9 and then times 10, so that's not that many, right?
Yeah, that is the configuration, correct?
Yeah, so I'm saying like the training data can contain all of that. Like the training data that we generate might as well contain all possible valid configurations.
Correct. Yeah. So that's the idea. So you generate all possible valid configurations. Now you train over some some 50-60% of that. Use the remaining for testing. You train your neural network. Finally, the verification has to be done on the neural network.
I think we're veering, towards correctness verification. So of course, verification has to be done by Z3. Here, the question was the entire training data he can generate somehow using his own program. I mean, the heck with Z3. That was the question.
No, I just read the assignment, and it says that the only valid configuration are those in which the number of x is 2 or 3, right?
Correct.
So there are not that much amount of configuration, I think.
Okay, doesn't matter. There are some number of configurations. Now, for every configuration, you have a possible player move for player one. And now this combination of a configuration comma the player move has to be classified as good or bad before you go to the training.
Okay.
Correct? Now this good or bad classification, we insist that you do using Z3. That's all.
Okay, and the number of configuration can be generated programmatically.
You can either generate it programmatically, you can use Z3, you can do whatever, but the classification you must do using Z3.
Actually, you will find, I'll tell you one thing. I think you will find it easier. If I were doing it, I will do it through Z3. Okay. But anyway, Madhukar has specified the assignment. So I don't know why. I mean, you think that doing by Z3 is cumbersome?
The way we do it using Z3 would be like by asserting more and more conditions after picking out the satisfying assignment that we do, right? I mean, that we get. Like once we get one satisfying assignment, we block that with another assertion.
Correct.
And then we get another one. And then it just kind of keeps piling up. So doesn't that affect the complexity or something?
Exactly. I was worried about the complexity.
Yeah, there's many Z3 calls, I do understand. But if you were to write a program, how will you do it? You will have to keep track of something as well, no? You have to enumerate it. Why will it be any less complex?
There we don't have to actually refer to the things that we store, right? Like we can just sort of like loop over all possible configurations.
Correct. So you can do that, but the classification part must be done using Z3. That's all that we insist on.
Oh, okay, then that's fine.
So that program will be simpler, is what you're saying.
Also, sir, the Hitar's code for this neural network as
yeah, but yeah, I know that you're insisting. I've been keeping, I keep reminding him. I don't know why he has.
Yeah, for the network, are we supposed to
maybe-
use the network that we used for the previous assignment, or are we like supposed to use some other thing?
I think you can use TensorFlow and use the weights.
Okay.
Yeah, you are asking Madhukar's, I'm sorry, Hitat's code for generating the formulas, correct?
Using Z3 to verify neural network, that code.
Yeah, so you remember that both Madhukar presented one, and
code is available, I think, but Hitas is not.
Yeah, that is fine. I mean, I do understand that. So, but you do have one, okay? So, you can use that to figure out the style. I don't know why Hitat has not uploaded. I will check with him. But you have an alternative.
I think Hitat's one also would be more helpful. It will be helpful, I guess.
To review it is what you're saying. Yeah.
Yeah. Means
I will again check with him. Okay. Any other questions before I move on? Okay, so here is, so last time I introduced the problem of SAT solving and and resolution principle and a procedure to decide proposition logic based on resolution, and a basic version of DPLL procedure, which was a more directed way of doing it, using one form of resolution called unit resolution, which was embedded in this by using Boolean constraint propagation. But it also involved doing backtracking. To just refresh your memory, I will go through an example here again, to illustrate what the basic DPLL looks like on an example, and how the backtracking is done when you hit a conflict. So the yeah, so the iterative method, I had a code which defined it as using recursion, and this is just a loop version of the of the code. So I will go into the example. You can see the example. I want to have both of them, at least for some amount of time today. Okay. So can you see the example? Is it clear enough on the right side? I guess it is. So Madhukar, is it clear? Yeah. So you can read the example. Madhukar?
Hello. Yeah, yes, sir.
Yeah. Is the picture on the right side clearly visible? That was my question.
Yeah, it's visible. I
Okay.
mean, it's legible. Yes.
Or do I have to make it? If I make it any bigger, then yeah, that's a little bit too
Yeah,
big.
one has to come closer to the screen, but yeah.
Yeah, yes. Yeah. So, or maybe I don't need the left one, and I can make.
No, this is fine. I think it is. It is. Yeah.
Okay. So here are the clauses on the left side, C1 through C6, and what. Yeah. So you would start with the BCP if there are some unit clauses in the input formula itself. Then you start with a BCP. Okay. Otherwise, once you have, since here we don't have any unit clauses, you have to make a decision on any one of the variables to create a unit clause, and then you add that to make a do BCP. So I choose to take decide on variable x1, okay, and I make x1 to be 1. So that's why I'm taking the solid side. There is also a dotted side here, so I'm exploring by assigning 1 to x1 at level 1. And when I do that, still C1, if I do once, there is simplification in C1 and nothing else, correct? Because x1 reduces to, the literal not x1 reduces to 0, and still, there are no unit clauses to propagate. Okay, so I'll have to, so all the remaining clauses are all unresolved, and therefore I'll have to make a decision on x8. Okay, I have to make a decision on some new variable, and I choose x8. Once again, I assign 1 to it. Okay, so that gives more simplification. X8 appears in the negated form in C6. For that, reduces to false, and you have, but still there are no unit clauses to create it to propagate. So you make a decision, a third decision level 3, and there I choose to make x7 0. Okay. Now this kicks off a whole chain of unit clause propagation inside the BCP. So if I make x7 0, then C6 becomes unit. And so a decision on x6 to be 0 is implied. Okay, so that's the the decisions that are derived by BCP are called implied decisions. So x6 bar means x6 is forced to be 0 through BCP, and that when then through C5 also becomes a unit because x7 is 0. So 0 is implied for x5. So now once x6 and x5 are made to be 0, so C4 becomes unit, and there's a, x4 is implied to be 1. And that makes C3 unit. So it makes x3 to be 0. And when you plug that into, let's see. So am I doing so? X4 is 1, therefore x3 is derived. So C1, by the way, what C1 also becomes unit because X1 is 1, so it forces X2, infers X2 to be to be 1, and that's what. And when you plug these two things, X2 1 and X3 0, into C2, X1 is already a 1, and therefore that literal reduces to false. C2 will reduce to false fully, and therefore you have a conflict. Okay, so C2 simplifies as a result of BCP and creates to false, and that creates a conflict, and that's what is happening here. So the outcome of BCP as a result of this decision on X1, X8, and X7 gives rise to a conflict. Okay, so once you have a conflict, that means that there is no satisfying assignment for this partial assignment to X1, X8, and X7. So what this says is then you have to backtrack. For a moment, ignore the analyzed conflict and so on. So the backtracking is you just go to the latest level and you explore if the other possible value for the variable assignment, and after which you will, so you're just backtrack one level at a time after exploring both possible assignments to a particular variable at a certain level. So this forces a backtracking. So to X7. So that's what I'm showing here. The conflict, it takes you back to X7. Now there is still the one value for X7. Assignment of 1 is unexplored, and therefore you go down the that path, the solid path. So making X7 to be 1, and then you backtrack, and then you do BCP again. So what happens is if you did that, you will notice that you will keep hitting running into the same conflict. Okay, so if I made here after X7, so it will simplify C5 and C6 to be. I'm sorry, when I make X7 to be 1. Flip the decision on X7 at level 3, I'll make C5 and C7 completely satisfied. They become true. So I'm still faced with making more decisions on more variables. So, I can end up choosing the same value that were inferred in the previous things, for example, for X5 and X6. If I do that, then the same kind of BCP propagation will happen, and I'll end up getting the same value as before that will force X4 to be 0, which is what was creating the conflict. Okay, in so the same kind of conflict can keep repeating. Okay, and that's what I'm trying to illustrate, and I'm illustrating here. Okay, so there is a satisfying assignment in this branch, okay? But before hitting it, depending upon the decisions that you make, you may have to explore a lot of different combinations before you hit the satisfying assignment, okay? And often what happens is that the same kind of conflict can be, decisions that you make, the wrong decisions that you make can take you into encountering the same kind of conflict, and which is what we want to avoid. Okay, so that was one reason why for a long time DPLL was, that was dominating this repeated conflicts, okay? And that is what is avoided by, so the idea is, if we could learn something from this conflict, what is the root cause of that conflict, and if something can be done to block that, the root cause creating that conflict. Here, the root cause for the conflict is that once you have made a decision of 1 for the variable x1, it so happens that x4 has to be cannot be a 1. It has to be a 0. Okay, so this formula is implied by your the original things. One of this has to be a 0. So if you could infer that, if you can derive this fact, if you can learn that fact, and then since that is a inferred clause, and that you added it, you could then, after the first time you get a conflict, if you can somehow analyze the conflict and then derive this, the clause that is the fact that that is causing it, then maybe you can avoid repeating this conflict. So that is the idea of the conflict-driven clausal learning, CDCL for short. Okay, so now let me make it bigger. So any questions here about the basic DPLL? Is there any doubt about backtracking and this? Okay, so if you have any questions, please ask now when we still have these pictures. So can I move on? There are no questions, I will move on. Okay, so here are the 3 drawbacks of the basic DPLL, okay, which is shown on the left side in as a recursive code. So no learning that I illustrated. It throws away all the work performed to conclude that the current partial assignment is bad. And as a result of which, you can potentially revisit, run into the same conflict, arriving due to the same reason. The other thing is the decision heuristics. Okay, which variable do you choose to decide on, and what polarity that you choose to decide on. So that also has a thing, and several heuristics that also take into account this learning strategy were proposed later, and that had a dramatic impact on the scalability of solvers, SAT solvers. The other important idea, breakthrough idea was, instead of backtracking to the latest level, and then then you would backtrack to earlier levels only after exploring all the if there are after exploring all the entirely the all possible assignments at a particular level that don't result in conflict. Instead, you could choose to skip levels to backtrack in a non-chronological fashion. So that's what. So that, and especially when you combine all these things with this learning strategy, they seem to give an enormous boost to the time taken to do the proof search in SAT solving. So these three things is what we will see, these ideas and what is involved in what entails them. Okay, so moving forward. So here is a version, a more advanced version of DPLL, which includes causal learning and also leaves it open for non-chronological backtracking. So what you have is F is the input set of clauses, the formula. So A is your assignment, okay, that you're accumulating. So you initialize, A is the set of assignments to variables. You initialize that to 0. So then right off the bat, you do a BCP to propagate all the unit clauses that may exist in the input formula itself. And if that itself returns, false, then you return false. Okay. Well, there is actually a case for true also here. If everything reduces to true, then you can do you can return true as well. So otherwise, if you still have two more unresolved clauses, then you will have to start making decisions. So you initialize a level to 0, which gives the decision level that you're at. So as long as you still have unassigned variables, you increment the level variable by 1, and you decide, choose a variable to decide on, okay, and add that decision as a unit clause to A, okay. Then you do a BCP on F union A, okay. So while there is conflict, then you have to do something. Okay, you analyze it. As long as if there's no conflict, then you jump out, and then you have a satisfying assignment. Whatever partial assignments that you have at that point is your satisfying assignment. But if BCP results in conflict, then in the basic DPLL, you would have just backtracked without actually doing analyzing the conflict. Here, there is a box called Analyze Conflict, which extracts a clause representing the root cause for the conflict. And that is C, produces a clause which explains the root cause for the conflict, and it also gives suggests a level to backtrack to, that is B. Okay, and what you do is then you add the conflict clause to the original formula. We will see that the conflict clause that it generates is always something that is implied by the original formula. So it is sound and safe to add C to that. By adding C to that, the effect will be to, the only effect that you have is to block the root cause of that conflict, and therefore your search space can hopefully be reduced. Okay. So, and if you've backtracked, in analyzing the conflict all the way to the root level, and you, and you haven't found any, assignments, then you declare it as unsatisfiable. Okay. Else, you backtrack to the level suggested by the Analyze Conflict box, and then you go back to the yes. So then you go back, and then you do backtrack. And when you backtrack, usually when you backtrack, you undo all the assignments up to that level and throw away all the BCP thing. Okay. Yeah. So, and you keep doing this, and then if there is no conflict, then you come out and then see if you there's still some unresolved variables. Then you have to decide and then go back into it. So, yes. So these are yeah, the two things that I mentioned. So what I'm going to do now is to go into this box, analyze conflict, and see what happens there to extract this clause, which is called a conflict clause. Although it's called a conflict clause, it really is a clause that blocks the root cause that is causing the conflict. And we also see how, so this part is very logical, okay? And there's no heuristics here. The non-chronological backtracking is not heuristics, but it is just a suggestion for how you could do CDCL even without non-chronological backtracking, as you will see. Okay? So any questions?
So is the decide FA function some heuristic to decide which variable we pivot on?
No, that's true. Now here, yes. So far we have just decided the variable to pick, to decide on, to make an assignment for arbitrarily, but we will see towards the end of this lecture some decision heuristics, especially one that had a tremendous impact and which has become almost the standard for doing it. I mean, most of them are variations of those decisions. But yes, you're right. The decide is also heuristics, heuristic based. Yeah. So that was the point that you raised. Okay. So it's the same example that I had shown you, and I repeated there only to show how the same conflict can get repeated in the basic DPLL, and that's what we're trying to avoid by generating something that explains the conflict, a clause that explains and also blocks the that conflict. Okay, so here so what you do, so I'm going to go through this thing again, not in this fashion. So the way that this analysis is done is, as you make the decision and do BCP, I mean, and make decision, and then as you do the BCP, you build what is called a graph, a dependency graph, and it's called an implication graph that explains the dependency among which clauses led to the various the implied decisions that by the BCP propagation. So we'll see that here. Okay. So this, everything that is shown in green here is yeah. So this is an explicit decision. This is a decision, and a red here. I use the convention red to say that as a result of the decision, that literal reduces to false. Yeah. So after that, you make a decision on X8 at level 2. That's what is indicated here at level 2. Okay, so that simplifies C6. Then you make a decision on X7 to be 0. This is when BCP kickstarts. Okay, so C5 becomes unit. So that's what. So as a result of this decision in clause 5 becomes unit and gives rise to this implied decision. So everything that is you make explicitly by decide is the is called decision literals, and the one that is derived by BCP are called implied or inferred decisions, because they are inferred as a consequence of the decisions that you explicitly make. So, and once X5 becomes, C5 becomes unit and you infer something on X5, that results in a chain of events. So in C6, X8 is already gone. So as a result of X6 and X5, no, what is C6? No X5. So X6 and these decisions, that becomes unit C6, and it implies a decision on X6, and that's what is being shown there. Okay, all these are a result of BCP, and all these implied decisions are at the same level as we are currently analyzing. Okay, so as a result of these two implied decisions on X6 and X5, C4 becomes unit, and it forces X4 to be 1. Okay, and this is what is causing the conflict. So X4 becoming 1 makes C3 to be unit and implies X3 to be 0. And once X3 is 0, in C1, due to earlier decisions, X2 will be inferred to be 1. And these two, along with X1, these two inferred decisions on X2 and X3 along with X1, when plugged into C2, it reduces that to false, creating a conflict. Okay, so as you can see, first of all, the implication, this is what is called implication graph. Okay, so this is by example. I formally define what an implication graph is in a few slides from now. So as a result of this, you can see it shows you, it gives you the inferred decisions and the clauses that have responsible for implying those decisions that are responsible for that conflict. And the analysis will be done on this implication graph. How exactly you will derive, okay? So what we derive out of this is that certainly once you've made X1 and X4, once you've made a decision on X1 to be 1, X4 cannot be 1. I mean, X4 being 1 is what is causing this, okay? And what the thing is, of course, X4 itself was, implied due to other decisions, but still, this is certainly one thing that you cannot. So you could, so not X1 or not X4, that will be derived as a conflict, a possible conflict clause, okay? Outcome of analyzed conflict. You will see that is not the only conflict clause, okay? There are multiple solutions for what can be defined as conflict clauses, and we will see how we decide to pick one amongst them. So here I'm just giving you an overview of what analyzed conflict does, and that's what it determines, picks one of the conflict clauses that possibly explain and can block this conflict, and also adds it to the original set of formulas. Okay, and that's what is done here, and decides to jump multiple levels and backtrack to level 1. Okay, I'll explain why what is the criteria for it to do it, and why that seems to work better in practice. And that's what I mean here. What happens is, you see, the reason why I say it blocks is because the moment, okay, actually it doesn't matter whether you backtrack to one or not. See, the moment what happens is when you add it and when you backtrack, this clause becomes unit. Okay? Even if you backtrack to the latest level 3, because x1 was already decided to be 1, the conflict clause and the way that a conflict clause is created will be such that the moment you backtrack, it will become unit, okay? And then forces the certain decision at the current level to be flipped, okay? And that's why it the conflict clause always has that property, and therefore it prevents x4 becoming 1 was what was causing the conflict, and it prevents that. Okay, and that is the crux. Now, yeah. So that is the overview of the thing. Any questions till now? So I still haven't explained how exactly you analyze the implication graph to extract these conflict clauses, and that is the next thing I will do. So this you already seen. Under given partial assignment, yeah, there are some assigned literal, which can be either true or false, and there are unassigned. So the red and the green are assigned literals, and so there are unassigned. Yeah, this you've already seen. So clause can be either satisfied, unsatisfied, or unit. Okay, so an implication graph formally is the vertices, it's a DAG, okay, that records the history of decisions and the resulting deductions derived by BCP. So every literal or the conflict node itself is a vertex in the implication graph with its decision levels, okay? Because the decision level information will be used to define the criterion for non-chronological backtracking. Yes, so that denotes the decision level at which it entered the partial assignment. So these are decision literals, and these are implied literal and nodes, and that is a conflict node. So there is a edge from V to W. There's no self edges. So if yes, and that edge is called an antecedent of the implied literal. Okay, so and this edge is the clause that actually implied this literal when based on earlier decisions. Okay, either earlier decisions at previous levels or decisions implied by BCP at this level. So that's how you do. Of course, a unit clause C is an antecedent if it's all unassigned literal. So you can have some unit clauses right there. I mean, right in the original formula itself. In which case it may not have an antecedent. Okay, that's what to address that case. So for those things, there are no antecedents. Okay. So, so is the definition of implication graph clear? So as you will see, okay, there are several things to note here. So all the incoming edges to an implied literal will be labeled with the same clause, okay? Because I mean, that will be implied by all these things getting plugged into a particular clause, correct? And that's, you will see, all of them will be named. And sometimes, you know, you can even have only one edge going into a thing if the clause only have two, has two literals. Okay, so that is one thing. And yeah, so here just so what are the clauses that give rise to this implication graph? Well, the ones that are listed there. So from the original, yeah, so you can actually create the clauses from here itself, correct? Because to C1, you know, by X1 deciding, even though without looking at the original one, you can actually construct it, and that's the point that is being made here. So if, since plugging this one by itself create implied X2, it has to be, C1 has to be a clause which has two literals, okay? So one of them, in plugging X1 would make one literal, that literal go to false, and implied X2, so on, okay? So C2 should be?
We should have a clause like X1 and or not X5 or not 3, or 3.
Or X3, correct.
Yeah.
The negation of the previous thing, the the previous assignments that go into it, and or X3, and so on, okay? And you will also notice one other thing. So every, the clause for every node here, internal node, other than the source, you have that literal, for example, literal X4 here appears in opposing polarity in C3 and C4. See, X4 has to appear in opposing polarity. The reason is that it actually, if it were to force this, so you know, something in it is forcing, in C4 it is forcing that to be something, you know, different, okay? So because it is implying X4 to be you know, one in this case it's a conflict. So it's, yeah, so you will see that this one has to appear in opposing polarity, because you know, it caused it to, it implied this decision, correct, on you know, with S3 being when it was plugged in, it imposed that, okay, and you know, when it was plugged into C4, in this case it was a conflict, and therefore it made that go into false to infer some other you know, so X4 will appear there and it will make it to go to false, okay? So here it made it to go to true, and here that will simplify to false to imply a further chain of decision. So that is another property that is satisfied for every interior nodes. This is true. For example, in C2, C4, X3 appears with opposing polarity. Okay. Yeah, I think this is yeah. So this is just interesting because there is you know, you can compute it the same way, and the only thing is CK, you just have to, there's no you know, antecedent, therefore you just have to put that unit clause. This is a case where there was a unit clause in at level 0, which means there was a unit clause as part of the original formula itself, okay? And so that led to a DCP at level 0, okay? And that's why this one you know, has only an outgoing edge. That was the only purpose of illustrating illustrating this. Yeah, I don't think I have missed any other point to make. So any questions? I hope you understand implication graph, okay? Okay, so now I will get to part where how to extract conflict clauses. Yeah, so a conflict clause formally is something that is implied by F, and it blocks the partial assignments that led to the correct conflict. By the way, from a resolution point of view, what is happening here? So these were the decisions that you made, okay, at different levels. Okay, so what's happening is if you added these decisions as unit clauses to the original set of formulas, that there was a resolution proof that led to a contradiction. Okay, you can actually check, and this implication graph is not exactly a resolution graph, but it has the same information inside it. Okay, and so that is same. So a conflict clause is something that is implied by F, and it'll block this partial assignments to the decision variables that you have made to the conflict. That's how it is defined, and you will have to derive that. Okay, so a pictorial way of doing it is any cut in this implication graph. Okay, there is a cut. A cut of a graph is something that partitions a graph completely into two disjoint set of nodes. So a cut that, I have a definition here. Every cut that separates, so here are the sources. The sources of this graph are the decision literals. And there is a sink, which is a conflict clause, okay, C2. Okay, and that's the conflict side of the graph, and that's the other thing is the source. So any cut that completely separates the conflict side from the source side by cutting those set of edges. After cutting those set of edges, what you have on the left side, okay, a disjunction of that will form a conflict clause. Okay. So, and you can see that, so this is the original, of course, the original set of decisions. You take set of decisions that you take, the conjunction of those decisions, and you negate them. That gives a clause, and therefore, that is obviously says that, okay, whatever decisions that you made, that in that set of decisions cannot be, has to conflict with your original set of things, and therefore this always is something that blocks it. Similarly, if you have, see, the one that we noticed was derived earlier, gave as an example, is a result of this cut. Okay. So a conflict clause always have one or more of the sources, and it has, one or, yes. In this case, yeah. I'm sorry. This, yes, correct. So this one, yeah. So the literals that go into it are the nodes that are at the rightmost end of this thing. Okay, from which the arrows that you cut are going. Okay, so that's why you have x1 and x4 literal being included in that. So here the cut is the nodes that are at the source of the edges that are eliminated is what that go into forming the conflict clause. So intuitively, so what's happening is, see, as a result of these decisions, all these these are inferred decisions, and they do play a role, okay, in doing it, in creating in creating this, this conflict. Therefore, so here, this X4 here kind of covers all the implications of the inferences that are made by the consequences of the decision made on X8 and not on X7. Okay, so the decision on X4 and this implied decision that were made, because X4 kind of covers all these things. So that is also so that's why it kind of dominates the reason for the conflict. Okay, so can you guess another cut that is also possible here? Another possible cut of this that can form a conflict clause. So is this definition of the cut clear to you?
Yeah, so if we cut along, say, the C1s and the C4 edges, would we get a conflict clause?
Yeah, that's right. So you can go make a cut by cutting C1 and the C4 edges. Yeah. So that will give rise to a conflict clause that has the literals not of X1, X6, or X6 or X5 also. Okay. And you see X6 and X5 cover X8 and X7. Okay. And that's why by including these things, you don't need to include those those sources, because not X6 and not X5 were implied by these decisions. So therefore, they dominate over X8 and X7. So yes, that is also a conflict clause. And you will see one of the criterion for choosing X1 over X4, X1, not X1 or not X4 over the other things are that it contains something a little which is called a unique implication point. Okay, I had a definition. Yes, I mean a unique implication point is any node in the implication graph other than the conflict that is on all paths from the current decision literal to the conflict. Okay, so here, for example, X4 is one such node. Of course, the source node that represents the decision made at the current level is always a unique implication point, because X4 is a unique implication point because from the node that represents the decision made at the current level, all paths going from that to the conflict node passes through X4. And the source node, of course, has to pass through. And that is the criteria that you use. And of course, this is also X7, the node, the source node, not X7 at 3 is also a unique implication point. But we choose this over the other conflict clause that contains all the sources, is because you choose, it's better to choose the one that has a unique implication point. There are multiple unique implication points that is closer to the conflict side. Because as you can see that this is, firstly, the closer it is to the conflict side, the smaller the conflict clause will be in general. And it also, it kind of encompasses all the more decisions that it encompasses more of the reasons that actually led to this particular thing becoming one, which was responsible for the conflict. But there is also another important thing. So this is the first unique implication point. I mean, certainly having a unique implication point is good. I mean, let me backtrack. Okay. So you see, if you have a unique implication point, then what you have is the conflict clause will have that will be the only literal at this, whose decision, either explicit or implied, that was made at the current level. Okay. Yeah, so that is the reason. I don't know if I'm given that. No. Okay. Yeah, so I should say that. Yeah. Okay. Here I will go back to explaining why having choosing a conflict clause that has a unique implication point as part of it is better than the over the other thing. Okay, so let me doing. I think I have an example to illustrate that. I'm going to make this smaller. Maybe I don't need it right at this point. Okay, let me first describe how you derive this, okay, and then illustrate why unique implication points are better. Okay, so let me go back to. Okay, so you can actually use a resolution to derive. So this is the actual detail inside analyze conflict. Okay, and yeah, maybe I should go through that example. Yeah. So yeah, well, I'll illustrate one thing. See, I already made noted that the for every node, the incoming, the C2, the incoming and the outgoing, they have that literal in opposing polarity. Okay. So what is causing the conflict here? Obviously, X4, this X1 decision on C1. The decision of X1 and X4, implied X2, and the decision on X2, resulted in that it was in opposing polarity in C2, and a plugging of that was led to the conflict. Okay. Now the question that you should be asking is, how can I derive something that makes, obviously, these decisions that resulted in a conflict between C1 and C2, okay? So this implied X2. So therefore, the question is, how can I make this conflicting decision on X2 implied by C1 and when it's plugged irrelevant, okay, for doing, how can I do irrelevant? How can I make it irrelevant, okay? So, okay, if I did that, then what does resolution do? Whenever you resolve two clauses on a particular variable, you always get something that is satisfiable, okay? I mean, you always get something that makes the conjunction of those two things satisfiable, regardless of what assignment to X2 might be, because X2 appears in opposing polarity in these things. So if you take the resolution of C1 and C2, that gives you a clause that ensures the satisfiability of C1 and C2, irrespective of the decision, the implied decision on X2, because the decision that was implied by C1 on X2 is conflicting when you plug it into C2. So that's the idea. So you actually use resolution to get the conflict clauses. Okay. Having said that, before I go into describing this algorithm inside analyze conflict, let me use this picture. Okay, I know the third picture is a bit fuzzy. Okay, this is the same set of clauses I have here. So the way that you do is, okay, so I'm assuming you have the implication graph, but you actually don't need the implication graph per se. Bear with me. So I don't think you will need that. Nonetheless, let me keep it. Yeah, so here I've shown the sequence of resolution steps. Okay, so you start from here, from the conflict side. Okay, so the antecedent is the antecedent of the conflict node itself is the clause that led to that resulted in the conflict. Okay, so you start with that, and you take and this is the order in which the implication was, and I'll make it a little bit bigger. Okay, so you need to keep an order, an order in which the implication itself was propagated, because there can be you have to keep it, you have to keep track of the order, given the order in which the implication is derived by BCP. Let's assume it is this way. Okay, so there are cases where the implication graph itself doesn't tell you whether X5 was derived first or this implied decision on X6 was derived first, later. Okay, but it doesn't matter. But for the purpose of actually defining how you derive the conflict clause through resolution, you need to assign an order. Okay, for these things, for the way all the explicit decisions. The first three are explicit decisions here, and X6, X5, X4, X3, and X2 are implied decisions. And let's assume that it is in this implication order. So you start, and finally, the final variable on which you decided was X2. Okay, so you start with that. Okay, and then you choose, C2. You start with C2 and resolve on this variable X2 with C1. Okay, and with the antecedent of that. So antecedent of X2 is C1. So when you resolve it on X2, you get X1 bar or X4 bar or X3. Okay, so and then you keep repeating that. Okay, as a matter of okay, so every step of this, so then you get this, and then you check what the implication order is. X3 is the next to last implication order. So you go to X3 and check what the antecedent of that thing is. Here it is C3. And then you resolve between C3 and the current one. Okay, so you keep on resolving in that order the current clause that you have, which initially is the antecedent of the conflict clause, and you keep resolving it on the variable in that order. And until you, so as a matter of fact, you can keep on doing this until you get all the way to the source. And every step, the clause that you get is a conflict clause. Okay, and and as you can see here, once you do one more step, you get that desired one. Okay, so the algorithm really consists of doing these resolution steps on the clauses as I've defined in this order until you see a unique, a single literal at the current level, and that will be the unique implication point. Until you see a single literal at that is at the with the current level gets into your resolvent that you get as a result. So then you can stop, or you can actually continue is this showing this way? This moment, please. Okay. So here is the complete resolution, steps going all the way back. So each of these things is a conflict, a legitimate conflict clause that can block these things. The one here, X1 not and X4 not, happens to be the one that consists, contains the first unique implication point, and the one at the end contains the thing. And that's how you you get. So let's go back to the algorithm here. So this is what I described on the example is what is described by the code here. You start with assign V, the level of the conflict here, which is 3, and if that is 0, then you're done. Okay, then you have to just backtrack. Otherwise, you first initialize one of the clauses on which you resolve, you do the resolution on, to be the antecedent of the conflict node, which is C2 here, and then you repeat this thing. So you take the last assigned literal at that level. So that's where I use the implication order. Okay, so the last assigned literal was X2. So and then you take the antecedent and you resolve between the antecedent of the last assigned literal and the current clause. Okay, and you keep doing this until you get one literal at the current level inside it. Okay, and you see that's why I did not stop at X2, X3. Okay, so I'm sorry, at X4, X4, X3. So I continued to come to until there was only one thing at that level. Okay, so yeah, so that is the algorithm that you use. So any questions here?
So we are going to always find a cut such that, like, basically there is only one variable there which has been implicitly assigned.
Correct. Yeah. So the cut, I mean, I illustrated in terms of cut, okay, but that is not, how you do it, okay. I mean, that is not how it is the optimal way to do it. You can just do it using, once you have the resolution graph, you can start from the conflict node and then do it. And then moment you see one, because you are doing the resolution starting from the conflict side towards the source. So, the moment you see one unique literal at the current decision level here appearing, you can actually stop. Yeah, correct. Yeah, is that what you? I guess that's what your comment was. Correct.
So does adding the clause, it does not potentially maybe block off any possible assignments that could have been possible without, like, in our original formula, right?
No, it will not. Why? Because it is something that is a logical consequence of the original set of formulas. See? Because what am I adding here? Whatever I added, I'm getting as a result of doing resolution on a pair of clauses that belongs to the original formula.
Right.
So whatever that you get is, is a logical consequence. So why would, this is not affecting any explicit decisions that you're making, but what it is doing is, if there are certain, it is forcing certain things. Okay, when you add, so let's see this. When you add X1 plus X, not X4, and then you backtrack. Okay, so in this case, you were backtracking to, the latest level was 3x7. So suppose you're not even using non-chronological backtracking. So what happens is, when you add this, it'll force the x4 to be, to be 1, which was the root cause of 1 that was causing the conflict. So it is blocking only those set of decisions that give rise to a conflict. Okay, so there is no use in doing it. It is not blocking any possible satisfying assignments. Okay, that is the important thing to note. Therefore, if there are no satisfying assignments at all, then you will end up either blocking all of them if you indeed continue to do it like this. Yeah. So then they'll be empty. So it is never blocking any potential satisfying assignments. Okay. Because you're doing this processing only on the graph resulting from not only the original subset of the original set of formulas into which these decisions have been added. Okay, these explicit decisions have been added to get a subset of the thing. So that is yeah. So the theorem, you could say, that gets the guarantees the soundness of it.
Right.
Okay, so the point, one more point that I want to make, the important thing is why this, among all the conflict clauses, why one which has with one that has a unique implication point is better. Okay, so I'll take another 5 minutes and I will end. Suppose that you chose x1 bar plus x5 plus x6 instead of x1 bar plus x4 bar. Okay. And then say you backtrack. So the thing is that the moment you backtrack to, backtrack, say to the latest level also, or even, yeah, to the latest level. So you keep x1 decision was made at law way before, okay? So that decision, if you add, when you add this conflict clause with unique implication point, it is sometimes what is called an asserting clause. It always, the moment you backtrack, it reduces to a unit clause, okay? Because all the decisions that you made at earlier level, this is the only one, it has only one literal whose decision was made at the current level. All the rest are decisions made at the earlier level. So when you backtrack way, above the current level, therefore it forces the to flip the decision on the sole decision that was, on the literal that was causing the sole literal that was causing the conflict. Whereas if you add something that has multiple literals at the current level, not a unique implication point, like x1, x5, and x6 here, okay? Then when, after you backtrack, this conflict clause that you add will not reduce and become a, will not become a unit clause. Therefore, you still have to make decision on x5 and x6, okay? So let's suppose here you backtrack to the current levels, where x7 was, decision was made. So these two will be gone. So you will still have, you'll be forced to make 6.5 and 6.6 will be gone because you're keeping the decision of x7 to be, you flip the decision of x7 to 1. So you still have to keep the decision on, you make a decision on x5 and x6. So you could end up making the same wrong decision, okay? Whereas if you have the conflict clause which has exactly one, then it will give you, it'll make the, it'll flip the decision, okay, in the right, in the right way. And that is the reasoning, behind doing it. So it will block, okay, don't get me confused, it will still block the current, no matter which conflict clause that you add, it blocks exactly the current kind of a thing, the current conflict. But the same kind of conflict which is resulting out of X4 can be, you could be getting it in other ways, okay? But by adding this one, the several consequences. See this, when you have a unique implication point, it covers a lot of different combinations of the things. But if you don't, then this will it will not be an asserting clause. Okay, so that's what, and therefore you could, yeah, that we already saw. Yes. Yeah, I mean, anyway, that is not explained here. So in the example, so that's the reason. So when you have add x5 and x6, you could end up, so the conflict clause itself does not flip the decision in your favor. Okay, although it does avoid this particular combination of your decisions, but by choosing X4, a clause that contains X4, you're covering that chance to what the decision that you make on. You still have to make a decision on X5 and X6 is avoided. Okay, so that is the thing. So that is on the regarding how you generate the conflicts. Okay. And the asserting level, what is the criteria that is used is, see, you could, after adding the conflict clause, just backtrack to the latest level, okay, which is also doable. And maybe, I mean, you may have, once you avoid this particular conflict, this particular exact conflict, so if you backtrack to this, to this level, then you may get other satisfying assignment which exists at this point. But the heuristics that is suggests is to backtrack to the second highest decision level of any literal in the conflict clause, other than the current decision level. So, for example, in this case, there was X1 and not of X4. X4 was at level 3. So it's saying backtrack to the earliest level that is less than the current level, which is 3, which is among, which is latest among all the literals in the conflict clause, which in this case, since there's only X1 here, it'll happen to backtrack to level 1. But if you choose the conflict clause to contain the UIP, X7 UIP, then of course you'll be backtracking to the current, you'll be backtracking to level 2, okay? And the reason for this is there's no logically justifiable reason. You could do anything, but it turns out apparently that if you backtrack to the earlier level with this new conflict clause that you have learned, when that is combined with certain other decision heuristics which are biased towards using the conflict clauses, that combination works much better in practice in steering the proof search towards the area which are less likely to create the conflicts. Okay, so that happens to be an empirical evidence, and therefore this criteria is used. Okay. Therefore, to summarize, two things. One is the way that the conflict clauses are generated is by doing repeated resolution on the antecedent clauses starting from the conflict side, like I described, until you end up getting a unique implication point, that is the unique literal, a single literal at the current level. And the decision level is as described here. So you look at all the literals in the conflict clause other than at the current level, and there'll be one, and pick the one that is latest among the decisions, literals that exist there, whose decision was made at earlier than the current level. Okay. So those are the two important things. So I think I'm running out of time, so I don't want to keep you too long. So I will end here and take any questions you may have. I'm sorry, I have gone way beyond the time. So I'll stop. If you have any questions before I stop sharing? Guess I packed too much material. Some chat note here. So let me stop recording.